clean up at that house with the water bed. He told us that ours was too small. But I grabbed the same.
Hey, did he say anything about our house that we chose? I had to email them.
Okay. He told us ours was too small. I'm tired of looking at houses on Zillow.
All right. So, hello everybody. Had a question just now that I'd like to answer for everybody. It's about kind of how should you prepare for the exam. So, just kind of where we are today, I'm going to start covering some of the topic that will really be the next section after the exam. So we're just a little bit ahead of stuff right now. Today's lecture is going to be the qualitative part of granular filtration. So I'm not teaching you like the math today, so hopefully that won't distract you for the exam. But it's kind of the concept stuff that will lead us to the math for granular filtration. Maybe we'll get into a tiny bit, but granular filtration anyway, it's pretty simple. So it shouldn't confuse you. I don't think it will. Thursday, you'll have the homework due, and we'll go through that homework and any other questions you have for the exam. And then a week from today will be the exam. That's the plan. So in order to prepare for the exam, what I would encourage you to do is go back through and essentially grade your assignments as if I was grading it for credit, and assign yourself some sort of a grade. And I'm saying this because this is the first time I've not actually assigned grades. I'm doing completion, right? So you can go back through. If I haven't posted just yet, I'll make sure to do that this afternoon. The solutions to the first homework set. Let me just see if I did that. I'll post it here, right under it, or right above the homework one. I'll post those slides that I went through, so you'll have those to study from and check from. You also have the recording. I will also post that. I did make sure to download that, so it's not going to expire. So I'll post that to YouTube and place a link there as well, so you'll see if you wanted to go through, okay, how did I do this problem again? That'll all be there with the recording. So that'll be there for you. And I suggest you do that with both homeworks, or at least check to see, okay, did I ace that problem? Great. Stop. I'll do it again later, on a similar problem. Oh, I had trouble on that problem. Let me stop and really dig down to figure out where did I go wrong? Do I understand? And correct yourself that way. So that's my general advice for the reviewing the homework. You can also go to this link here I have for you under the course main page. These example problems. This is going to bring up an Excel sheet, and essentially, I'll just grab that Excel sheet from a desktop actually. So that Excel sheet will give you some practice problems from our book, basically a listing here. Just a moment, I'll show you. And you can then go through and say, oh, okay, for this section of the course, we're looking at these different problems. And I would encourage you to go and try these as additional homework problems as you see fit. So if you know that you were struggling with a particular component, then go there. So you open the page, you see the segments at the bottom for the sheets. Go to segment 1 for this first exam. We have a book example, so this is like example 1.3 or something. And that's an example that the book gives you the solutions to. So the solutions are there. Definitely a good idea to review those. Sometimes I do take them and change them or whatever and give those as an exam problem. Then you have the problems in the back of the chapter. So if you know that you're struggling with mass balances, go here, do some of those, kind of sort out, challenge yourself to try some of these and see how you feel about them, right? If you're recognizing that chemistry is, really a headache right now, go through and practice some of those, right? So use this as a resource. When we get to the coagulation, flocculation, and sedimentation problems, these guys are here. You're also welcome to contact me for office hours. My plan normally is that I'm usually in my office Thursdays at 11 before class, probably also Tuesdays. So you're free to come by then, and I plan to have that space for you. But I'm also open to make appointments. Right? I could do Zoom. I could just set up a time. We can arrange something. So if you find yourself struggling on a particular topic, just come see me. Right? We'll talk it through. figure out where you're struggling with the problem or the process, and we can hopefully clear things up. On future exams, of course, for the second segment and so on, there's more problems here. Second one, I don't have as many because I really use more membrane stuff from another book. I can give you a little bit more resources there. Some of the chemistry for disinfection, we can call back to segment 1 for that. So I could repeat that there, but I think you got the picture. And then there's more for the final segment. So, all right, does that make sense? Any questions with that? All right. Okay, so that's the plan. So Thursday we will go through the second homework. It was a little shorter. It's kind of just on these physical processes. I would say the filtration generally is, for the most part, considered physical. So we kind of lump it in the same sort of category, but we're going to have this on the second exam, like I mentioned. So filtration we can think of in two manners. Today we're going to go through the granular filtration, but we can also consider membrane filtration, and we will. And the difference here is really, for granular filtration, what we're talking about is essentially we have a bed of sand or sand-like material that, we could, maybe if I'm going to draw it with a little bit of accuracy, we can draw it as like a bunch of grains packed in a bed, and then we have some water stacked up on top of it, pushing downward with gravity to flow through and be collected, right? So that's the plan. It's essentially just like groundwater, right? Groundwater is constantly moving through porous media, whatever sand or gravel or soil grains stuff there is. And in our water treatment case, we just carefully control it and make sure that we have good, precise control of what kind of media there is there, that it's not going to escape and contaminate our water or clog up the pipes or whatever, and that we have good control over it so we can properly clean it as it accumulates dirt. So when we think about granular filtration, then it's not actually a matter of size exclusion. So it's not working the same way as like a screen porch or a membrane would when we have a particle that's flowing through the water, or a mosquito trying to get through the screen on your porch. And essentially, in this case, what happens is the particle is just too big and it gets stuck and can't go through, right? So that's size exclusion, meaning it's just physically too big to go through the membrane. So we'll talk more about membranes in a few lectures after the exam. But essentially, we have size exclusion on the one hand, and then we have this granular media stuff, which can do size exclusion, but we're not really expecting that to be the primary thing. If the particles were that large that they couldn't fit through like sand, then they probably were sedimented out. They probably would have been removed just by sedimentation alone. So instead, what we're looking for is actually a combination of different little processes, things like adsorption, or maybe the particles, as they're flowing through the little channels, they literally sediment or perhaps impact onto the sand grains, okay? Or whatever granular media we're using. So it's kind of a collection of physical process. They stick to the surfaces. Maybe they start sticking together, as we'll see in a second. And any of the particle destabilization we achieved with the coagulation, that's going to help in this part too. So sometimes certain operations will take coagulation, skip sedimentation, and just go straight to granular filtration. If there's not too many particles, it may make sense, just because as these particles are working their way through, those same destabilization techniques are really helping the particles to stick. So here's just a little graphic to help us understand this. Like I said, this mechanical screening is not really our target. If that was the only way to filter them, all the pores would get clogged, and then we'd just get like no flow through it, and it would be a problem, right? So sometimes that'll happen. There's going to be a few particles that just can't make it through. Somehow they're in the water and they'll get rejected. But most of the time, what we're going to have is something like either particles flocculating together. So we have these individual little particles here, and as they're traveling through, they stick together and make a larger particle. So all three of those came together, met at some point, and now they're too big to carry on through, and so they'll stick to the sides. Maybe they are literally sedimenting as they're making their way through. So we have this particle here, it's traveling downward, the flow moves to the side a little bit, but it's slow enough that just literal sedimentation makes it drop onto the next sand grain, and it sticks to the surface. Okay, and it's removed in that sense. It's removed from the flow. If you think about it, if this happens and then you just keep flowing water through forever, eventually it'll make its way out. So we can't operate these forever. We're going to have to flush these particles back out and clean the sand grains eventually. Same deal with interception. Maybe we've got these little particles moving along with the flow, and then it's just scooting along beside the edges here, but the particle just kind of clips the edge of the sand grain or whatever, and it's intercepted, so to speak, and grabbed out of solution and just sticks there. Okay, you could also have impaction, which is a lot like sedimentation. The water's moving along, it moves to the side, and the particle doesn't move fast enough with it, and it crashes into the next granule. So any of these processes, a lot of them you can kind of say are basically the same thing. So this guy ends up here, so it didn't move out of the way in time. Any of these fizzy-sorption type processes are perfectly viable and expected to be happening. So all sorts of little things like this. So that's kind of the removal technology in a sense. It's just you throw it in there and hope it sticks. And it's pretty effective, assuming we operate it properly. So that's kind of the fine scale view of it. And a lot of what we'll talk about today and a lot of the math that we're going to do for granular filtration is really about how do we operate in such a way where we can clean it back out, have the backwashing steps with enough frequency, and manage the entire system so that we know that we're going to have dedicated backwash time and we have enough flow and enough backup filtration to do that, take these entire units offline for periods of time to do so, for maintenance and whatnot. Okay, so in terms of granular filtration, there's a few ways to do it. Most of what we'll talk about is like having a bed type reactor, but I just wanted to highlight real quick, there's also what we could call as like column or like a packed column. So over here, these big columns, those are granular filtration units. These beds are in these cylinders, and we can apply a little bit of pressure that way, more so than if we just have a flat bed. I've actually got some of these in my lab. These are just kind of a pilot scale granular media systems where we can put a little bit of pressure. The columns themselves, keeping it like a tall, thin cylinder, keeps the sand grains a little better compact and can handle more pressure than if you just leave them as an open bed. The problem with the open bed, if we put too much pressure, eventually the sand will just get pushed aside and you'll get a fissure and water will just go straight through, and then that's a problem because then you're not treating the water. So it gives a little more pressure potential, and if anybody's interested, I could walk you over to my lab at some point, kind of show you how those go. So I'll get back with you about that probably after the exam. So they're kind of neat. Right now we just have them hooked up to the tap. This piece of equipment was donated to us by a company that wanted to donate it for instructional purposes. So I'd like to show anybody that's interested. We can do the backwash step and watch the granular media sort of float back upwards as we're pushing water backwards through it. It's kind of neat. So we can get a little bit of hands-on with that, even though we're not doing a project with it, but it's still pretty neat. Okay, so then, I hit B, blank screen. So normally we'll have these granular medias in some large bed-like chamber. So it'll look a little bit like this. You see this construction working down there. This is probably a cubic meter or so of granular media. If you think about it, that's going to be a lot of media. It's going to be really heavy. So the good thing is we design these so that we reuse this media basically forever, right? It's just these tough granules. We make sure that we're keeping them there, not letting them escape. And then we can just reuse it. right? So unless we are not properly backwashing and cleaning it, then they should be reusable indefinitely. It's just sand, basically. Usually it's very carefully controlled sand grain sizes. Sometimes we could add anthracite or some other mineral or like activated carbon, something that gives us some maybe chemical adsorption as well, or something, maybe just change the characteristics. You can have one layer that's a little bit more dense, smaller pores, one layer that's a little less dense, it'll float on top, larger pores or something. So sometimes they'll mix it that way. And then when you do the backwash, they end up resorting because you're essentially letting them sort by density again when you're backwashing. So there's kind of some neat things you can do, but overall it's a bunch of sand that you're pouring water through. Right? So it's kind of simple at the end of the day. This would be a picture of some in operation. We'll look at a couple of videos as well, but essentially this would be one bed right here. And they're often operated in pairs, as we'll see. But essentially, you have some catwalks and maybe some water distribution across different areas. And then just the water just continuously piled on top of the bed, and then the gravity is just pushing it down through the bed. So that's sort of the basic premise. Okay, so just a quick bit about the terminology and history here. So one of the oldest water treatment technologies is pouring water through a bed of sand. Back in the 1800s, people started doing this, noticing that if we have some water that's not so pleasant, you could let it pour over a large bed of sand and just kind of sit there for a long time, and it seeps through, and the resulting water is a bit cleaner, better quality. And those were called essentially, well, these days we would call them a slow sand filter. And that was actually more so of a biological process, because it would be on the order of days for the water to make it through, rather than what we would call rapid sand filtration. So what we are learning about today, this granular filtration, we would call that rapid or rapid sand filtration. So you'll see that kind of terminology a lot. That just means we are using this filtration as a kind of we're continuously loading water on. The water's going to make its way through pretty quick, and we're grabbing those particles like we described, rather than letting it have enough time for biological process to consume waste products and junk that's in the water. Because if you let it sit there long enough, you'll get the biofilms, you'll get stuff growing, and we could treat wastewater that way in some sense. So if you had like river water and you had no better way to treat it, 1800s or something, maybe that would make sense to let whatever biological growth on these sand grains can eat whatever organic matter's in the water, that actually may improve the water quality and also help whatever bacteria to be there, hopefully to just be kind of natural, non-pathogenic bacteria, not related to gut, some animal's gut, right? And that extra biological activity would give the water some time to be exposed to maybe other organisms that prey on bacteria. So the only bacteria remaining would just be the ones that are just kind of growing there and eating stuff, you're not disrupting humans, hopefully. So it would help a little bit. It would not be a foolproof thing, but it should help a little bit. So anyway, with our rapid sand filtration, there's a few terms I'd like to talk about so we can kind of discuss the total life cycle of a filter, or the total operational cycle rather. First of all, we have filter ripening. So when we looked at those grains and we think about how particles start getting stuck in different places. If you just draw enough particles here in between the pores, you'll start realizing that at first, when these granular media are clean and free of dirt, there's actually a lot of open space. But as soon as you get a few particles settled, and maybe the granules themselves sort of shift and settle a little bit themselves after a few minutes of operation, they start performing a lot better in terms of separating particles. So early on, right after we start with a very clean granular media, we don't get very good separation. It takes a few minutes, maybe 15 minutes, of operation before things settle in and start removing well. So that's what we call ripening. That's kind of a warm-up phase, and it's pretty important that we do that every time we backwash. If you've ever taken like a Brita filter and the first few minutes of using it, it's like brand new, you're going to get these little black specks of activated carbon is what it is, coming out into the water. It's sort of a similar thing, right? You have maybe some dirt particles that were there before, or maybe in the case of the Brita filter, maybe some small particles that were just never going to stay in there. They're too small. They got jostled around. You want it to all settle into place and be stable before you're using it to produce clean water. So if you just backwash, you've got all these particles, most of them left, but some of them are just ready to come back out of the filter. You want to rinse it first or ripen. Okay, so then there's backwashing. Obviously, we're going to flow water backwards through the granular filter, push all these particles out. We're not going to flow it so fast that we lose our granular media, sand grains, but they're pretty heavy, right? So we can use that sedimentation for the granules themselves, pushing all these smaller particles up, out, and away, and collect that and send it to wastewater for treatment. So that's pretty obvious. Sometimes we'll take some time to do an air purge. So we push air up through these granular media. That really helps to rattle all the particles off the granules. And so we'll often do an air purge and then send water up through. See a video of that in a few minutes. So that's backwashing. Essentially, that's the way we continually reuse these filters without worrying about the particles eventually making their way out, right? Because that's kind of the thing we want to avoid most. Okay, head loss is another term. Essentially, when we add water to these filters, as they fill up with particles and get junked up, then it's going to require a little more pressure to push water through it, because essentially these pores that water is traveling through are getting smaller and smaller because they're filling up with particles. So we have to apply more pressure, and typically for a granular media bed like that, we're going to apply more pressure just simply by letting the water stack up a little higher. So we're getting more height of the water, so that means more force from gravity pushing through. And so we can measure that head loss really just by looking at what level of the water is above the media bed. So that's called head loss when we have a higher pressure drop. That hydraulic head required is increasing from what a clean filter looks like. Finally, turbidity. I think we probably mentioned it before. Turbidity, I'll explain here. It's a measure of how many particles there are in solution. We look at this just by seeing how much light is scattered away based on those particles. So we talked about it, I think, in sedimentation. And so we can monitor turbidity after the filter to make sure that we are not having a scenario where particles are escaping. Because if turbidity is increasing, that means particles are escaping. That's not a good thing. And maybe then we need to say, okay, we're going to stop operation now because it's time to clean the membrane or the filter. Okay, here's my slides on turbidity. We've talked about it before, but now I have a few visuals to show you. So obviously clear water on the left here, then more and more turbid as we go to the right. So maybe we wouldn't want to drink this water. So maybe that's already past our threshold of where we're acceptable for turbidity wise, but you can definitely see, okay, over here, maybe this is what it looks like when we backwash the water, right? So this is just a very clear example of water that light is not being scattered on the left, and it's progressively more scattered so that you can't even really see very far into the solution on the very right. Again, that's different than if you were to add some food coloring to color it, not scattering the light. If you want to measure this, at least in natural systems, a lot of times what you use is this Shecky disc, or however you say that. And essentially, once you can no longer distinguish the lines or have clarity between, you can kind of measure that distance, how far you can see a standard object like that as an example, and that gives us some, it's called nephelometric turbidity units. You kind of look like that, and once you can no longer kind of clearly discern, you can, I guess, have some sort of a training or manual or something to tell you exactly what to look for. But that's a way to visually see pretty easily, okay, this is how far you can go without light scattering affecting your vision through the water. So the visibility in the water, essentially. Okay, so how do we use these different parameters then to guide our operation? That's kind of the question here, because when we look at our operation, what we want to do is make sure that we are keeping ourselves safe from discharging dirty water down the clean water pipe, right? We don't want to send particles down. So how do we know how long we can operate before we have to stop and backwash? Well, there's really three methods, and usually it's a combination of two. So either we can go with a head loss limit. So at some point we have too much pressure, and we are either concerned about causing fissures to form in the sand media like I mentioned, and say, okay, well, we simply cannot go above this threshold because then we're going to have potential to have escape of particles. Maybe we use a time limit. And we say, okay, well, just based on operators' experience, it never goes well if we go past 72 hours. Okay, maybe it's something like that. So oftentimes this will just be kind of you maybe call it heuristic or just practical knowledge or experience. And then the last one would be a turbidity limit. So as soon as you start seeing too many particles come through, ideally this is like before there are very many. So hopefully it's just kind of a slow increase. If you have a sudden spike, there's a big problem, right? Maybe fissures happened or something. But generally you could see like a small increase over time. Some of the particles start making their way through. So this would be probably used in conjunction. You'd normally have this as kind of a safety factor, right? So you should have ongoing turbidity monitoring. So we'll say sort of a safety measure in a sense. Maybe you use normally a 72-hour limit, but if your turbidity ever reaches your limit before that, you just stop operation and you go ahead and backwash. Something like that. Like I said, you can use a combination, I guess maybe even all three at once. So if you had a cycle and you're looking at your time in hours here, and let's say you just cleaned the filter. So you'll say this is a clean filter, and we're starting the cycle. Well, the first portion, and really this would be like 15 minutes or something, this would be rinsing. So I'll just write it here. You're going to be rinsing or ripening, and your turbidity is probably going to be kind of above some limit here. And then it'll start decreasing. So if that's in like 20 minutes, I'll sketch out the typical cycle time a little more clearly in a minute. But just to kind of give you a picture here, if that's our rinsing stage, then we expect there to be a lot of particles come out because we just disturbed everything. We rinsed as much as we could out, and there's still some stuck there. So there's going to be some that comes through, and the media is just not operating effectively yet. And then we'll slowly operate from there for hours and hours and hours, and eventually we'll probably hit some limit, and we say, okay, well, that's too much. And so, we could say if we have some limit, I'll draw in red, where we say maybe this is our limit. If we draw this across, then we see here, okay, we've basically reached the limit, so we'll stop and say, okay, this then will trigger the backwash. And then technically we would backwash for, some amount of minutes. and then that would be cycle end here. And anything after we start backwashing, we're not actually monitoring the turbidity, right? Because at that point, we're no longer flowing forwards through the system, and so the turbidity monitoring is it's non-existent, right? So as soon as we hit that threshold, we would stop there. So that would be what it looks like for turbidity monitoring, and that's also why we see right here why we're not going to operate and use the rinse water for actual produced water. So that means we have some amount of time in between where we're just having production. And this is the good stuff. This is the stuff we want. We want to use it. We want to keep it. That's what we're aiming for, is the produced quality filtered water. Okay, so head loss would work pretty similar. In this case, maybe we have some sort of a limit, and we say anything above this limit is a no-go territory because we know that the filter just should not be operated past that limit. And so again, we could have kind of this rinse or ripening stage, and then let's just go ahead and label a backwash stage. And we'd start with a clean filter here. Let's go back to blue for this. This time, the head loss would actually not really follow the same trajectory. It would actually just start pretty clean, right? So we're starting with a clean membrane or filter, and that means that there's not really much adding pressure to it, right? The particles, if anything, we have the lowest, when we clean it, we have the lowest resistance to flow. So in this case, we would just start somewhere like this and slowly increase until we hit that limit and we say, okay, we've hit our limit, that's the time to stop, and we're gonna quit our cycle and backwash and do all that. So that case is a little bit more straightforward. Okay, so let's elaborate then on this cycle, because we have a couple ways now of dealing with how long the cycle is going to last. Could also just put a strict time limit on it, knowing that it never goes, we never, have a head loss limit or whatever, or maybe we use those as backup. We just say, okay, it's 24 hours. Every time 24 hours reaches, maybe like the first 15 minutes of that 24-hour cycle, that's our rinse. The last 20 minutes is our backwash time, 24 hours total, right? That could be our cycle, right? Or maybe it's 96 hours or something. It'll depend on, I guess, the amount of media, the type of media, and the type of particles you're dealing with, how dirty the water is. It'll depend on some things. If you have a very consistent source of water, maybe just that 36-hour timeline is just always fine, right? Maybe if you have rainwater disturbing a lot of sediment upstream, maybe you have to change it a lot. You really have to monitor that turbidity. So it's going to depend on the practical situation. But regardless of the cycle, if we have a start here with a clean, like a cleaned filter, then the first bit of time is always going to be the rinsing ripening. And this is often going to be 15 to 20 minutes, something on that scale. Doesn't take too long for the granules to kind of settle and for the filter to be ripened. And then we have hopefully many hours of filtration time. We'll call this production. So we're producing clean water. And this can be anywhere from 24 to, 100 hours, something like that. Doesn't have to be in that time frame. We could do something different, but that would be typical. I don't think you could get too much more than 100 hours. Maybe if you have a particularly clean source, I guess. And then you would stop at some point to do backwashing. And then if you have an air purge step, you do air first. So let's go ahead and say air purge. That would probably be 5 minutes if you have it. Then you would have your formal backwash. Which would probably be something like 15 minutes. Okay, so then your cycle is at an end, and you can just rinse and repeat, right? As if that phrase came from Justice. So that's your total cycle. So when we stop and look at this, and we think about, okay, how do I design a water treatment plant that can continuously filter water, but also these massive beds of water, filters that are producing tons and tons of water for us, we have to just completely stop operation for multiple minutes at a time. And we have to take some of that clean water we just made and push it backwards through this, because we need clean water to clean the filters, right? So we have to make use of clean water to backwash. And then we also need clean water to do the rinsing, because it's like we want to, when we're putting water through, we want to clean these and get them going properly. So that's water that we could have used, but we are no longer able to use, right? So when we come to the math, essentially what we're going to look at is how effective are they at producing water over the scale of the cycle time. So we could do a simple math on like, okay, well, how much water did we produce for 36 hours? This size filter, this flow rate, all that. We could get a simple term, okay, here's the volume. But then we need to add in like, okay, well, what volume did we subtract to backwash, and what volume went to waste with the rinse? Like, we have to go through each of those pieces and have a way to put them together to say, oh, okay, well, if we need 15 filters in operation at any given time, that gives us space to have 4 other filters offline to do their rinse phase and all that. So we'll take a look at, when we get to the math of it, it's really just doing some analysis of how many filters do we need? Well, given how efficient they are, how much time do we produce versus backwash, and what kind of loading rates and all that. It's just going to come down to that. So it's pretty simple, but it's kind of a pretty big deal for most water treatment plants, especially surface water. Almost always have granular media because, again, it's pretty cheap, right? It's mostly gravity doing the work. Obviously, we pump the water, and then it's a reusable media, and it works pretty well. So it's very common, very important tools here. Okay, so I've got a couple of videos. One showcasing the air purge, and the other does a better job kind of showing what it looks like over time as you've finishing the backwash. You can see like the particles are no longer there and stuff. So we'll kind of skip through the second one and watch most of the first one. I have to make sure that let me just a second. Make sure I get the time. One second. Gotta make sure I don't give you way too much noise, because it's the air purge is really, really loud and it's no fun. Just 1 second. Okay. All right, I'll turn off the lights a little bit. Let's do that. full theatrical experience for the exciting backwashing of the granular media. All right. Okay, so they're going to do the air purge first here. So you see they've got a little bit of water on top of the filter bed. Can't really see the media from there. But as the air is coming through, it's pretty nasty looking. So these troughs you see, normally when they're filtering, they're going to be adding water into this main chamber here on the left. And there's a bed on the right here and a bed on the left. And so then the water is going to flow into these chambers and then overflow into the bed, kind of giving a nice even distribution of water just throughout that whole thing. As we'll see here today, like in this moment, once I do the backwashing, the water is going to come, it's going to overflow into those troughs and then backwards through this channel system. That's just kind of the typical way they do that. And so you'll see it, in a sense, there's an automatic stop point for the water can't stack up really much any higher than any of that. I guess maybe you could if you pumped it in, but you're probably not going to operate in a way where your water's higher than that level, I would guess. So there's sort of a physical limit to how high you would stack the water in the first place. Okay, so they're just giving enough time for the air to kind of scour the particles here. And they don't actually take too much time, but then they have to, since they've been pumping air through the pipes, then they're going to have to prime them, and that's the really unpleasant noise part. I'll mute for you. So it should be just done with it. Okay, so we'll go ahead and just mute that for you. So you can see there's some people taking a tour or something, and you can see if I wanted to torture you guys, I could, right? cruel and unusual water treatment, right? Okay, so then they're just going to do that for a minute, get the pumps cleared, skip up head a little bit. So you see, this would be just two of the filter beds out of many. You can probably see more in the background.
Film the water for a bit. It's all warm. It's all bubbly. This is how they make root beer.
So you'll see what that person was talking about, making root beer here. So they're starting to. You see all these bubbles coming up. They're starting to. Actually, they probably haven't started yet, but they're. We're just starting to add flow. So it's been adding water, and now it's overflowing those troughs and flowing into the other one. There's your root beer. Joking, of course. So yeah, that's all the particles that were heading towards the drinking fountain, right? Unfortunately caught in these filters. Yeah, so as somebody said, that's disgusting. Now, some of this is actually the coagulant. So they would have been adding a lot of coagulant and dosing it that way to destabilize the particles. So some of it and some of the color may just be coming from the coagulant that was not removed during the sedimentation. So yeah, it's disgusting. Fortunately, that's all stuff that did not go down, continue through the water treatment. But certainly, definitely, you have to send that to wastewater. Some treatment plants, since you've got operators and everything, that kind of in the know-how, you might have an on-site wastewater treatment plant, or you might send that to a dedicated wastewater treatment system. And you can imagine this could be flowing in reverse for treating the water. It'd probably be coming through the same trough system and then adding onto the thing. So,
Louisiana homeowners pay close.
all right, so this one's a bit longer. We're not going to watch the whole thing, but I wanted to show it to you because right now you just basically have these granular beds, and you can see a little bit of a color change over here. I think you can see some of the bare media there, and then just sort of mostly particles and whatever else is on these. So I'll skip through a little bit, but essentially they're about to start backwashing. I think they just started the air scouring. Or they're about to start the air scouring. You can see it's a bit of a different design of the filter beds. You don't have the elaborate trough system, but you still have that kind of center trough feeding the two beds simultaneously. It's pretty common. And I don't know, maybe you treat this whole thing as one bed. I guess it depends on how you want to describe it. Either you're taking two beds off or it's just one filter bed. Okay, here we go. All right, so if you watch the watch what it looks like, it's starting to change. You can see all that rapid color change because it just started pushing air through. The air hasn't made it up yet, but the particles are certainly shaking loose. So, pretty impressive transformation there. Okay, so that's going to go for a little bit. Skip forward. And you see this whole video here is 18 minutes. That really is probably the full backwash time frame, right? So I could keep you to the end of class and make you watch the whole thing, but I'm not going to do that. So they stop doing the air, going to start pushing the water through. See it overflowing in a moment.
Is it a fixing that drives the water up? Like a hydraulic lift? Or is it
You're going to be essentially you have a pump on the underside because you normally have a collection pipe on the underside. It's a good question about like how's the water being pushed, and so essentially they're just going to reverse the pump and pump. They're going to take water that has been produced either by other filters or is clean otherwise, and then pump it backwards through it. So yeah, you can definitely see the. In this case, it looks a bit orange, so maybe it's a different kind of clay particle that's normally in this area, and it's just different geography. Maybe they're using a different coagulant. So the color of these particles is going to change based on sort of the treatment strategy or the what you happen to be using as a coagulant. So I'm going to skip forward like a couple minutes at a time, and you'll start seeing like, oh hey, there's less particles coming out now, right? You can start seeing it's a little darker patches. Still have these clouds of particles, but not as much. So it's certainly improving. I guess they're taking a look at some other stuff. So those are the other beds just in operation right now. And so when they're in operation, it should look fairly clean because it's just whatever water has already gone through probably sedimentation, and it's not like chock full of particles like this. So hopefully it looks relatively clean, and then the filters make it a little better. Certainly kind of neat to see just the water above these beds as you backwash kind of clarifying or clearing up a bit. Yeah, and the dark patches is probably just actually just seeing the sand or media itself. I think they're going to stop the backwash and start adding clean water or I guess water to produce back on it. So you see it's no longer taking water out. So all that water that was coming upwards is now just sort of piling on top. And they'll probably, I think they're going to reverse and go into normal operations. And then we can start to see the cloud particles go back in, I think. So at this point, they'd be ready to start operating again. And as you can see, like it wasn't an exact science of getting every last particle out of this water, right? And so there's probably still some particles in and around. So it makes sense then that we take the first 15 minutes or so of water produced by this now and send that to wastewater as well, right? So that's kind of it's an important feature of the system to get it working properly. Okay, so we'll leave it there.
Lights back on. Lines on us all.
All right, any questions or comments on that? Yeah. Yeah, that's a great question. So when you're backwashing in an open bed like this, there is a risk of losing your granular media through this thing, right? And if I show you the system in my lab, we could easily do that in this column system where if I'm not careful, it'll just shoot all the stuff right through because it's just the water's going too fast. So the typical backwash rates we'll learn after the exam. We normally backwash at about the same speed as we load it, or up to maybe twice the speed. But definitely the design criteria there is to make sure we're not losing our granular media. That way we can continue using it. So it's definitely a consideration, but usually it is like sand or literally sand. And so they're pretty heavy. Their sedimentation velocity is going to be pretty fast. And so there is that balance there. And maybe it would make an interesting exam question, right? How fast can you go upwards given such a sand grain or something? But yeah, it's a very important question. Anything else? All right. So we'll see you Thursday. I'll talk about the homeworks and any other questions for the exam. And have a good day.
How many questions does the exam